So today's lesson is on 5.B.2 exponential growth and decay models. Similar to yesterday, where we talked about, from Friday, where we talked about growth and decay with just increasing and decreasing, but they weren't giving us any kind of compounded interest. Now there's this word called compounded, where it's still interest that's being paid to an account, but it's happening more frequently. And so here's how we can represent that. So when we right here that this is called compound interest. It's interest that's paid on an initial investment, so it's the amount of money that you put into an account, for example, and this would be called the principal. We've been talking about the principal, or actually we talked more about A being the initial amount. Now we're going to use the word principal to talk about how much money you're putting into a bank account. So let's say you have $1,000 from, saved up from something. You're going to go put it into a bank account and you want to accrue interest over time. You would then check with different banks and see how often are they going to compound the interest. That means how often are they going to put interest into your account over time, and that you want to have more interest earned so that it would add to your initial amount. So here's the new formula that we're going to use aside of the one that you saw on Friday. It starts with A equals and then a P for that principal again, which we'll go through all of the different letters here in a second. Then in parentheses after it, there's a 1 plus, and it's a fraction here, r over n, and then for the exponent, it's an n times t. Okay, so this is the whole formula. You do not need to memorize these formulas or models. They will be provided to you, but you do need to be able to work with them and know when to use which one. So we're going to always use this equation here anytime you see the words compounded with the word after it being one of these from the table. So it could say compounded yearly, compounded semi-annually, compounded quarterly, monthly, weekly, daily, and it'll have an amount here for each one of those. So we'll get to this in just a second. First, let's label all of the variables. A stands for the final amount. It's kind of like how the Y was from Friday's equation, where it's like how much do you end up with over a certain period of time. So the final amount is A. P is called the principal, which again, this is kind of like the lowercase a that we saw with like our equations for increasing and decreasing models. Principal just means your starting amount. How much money do you start with before the interest is getting added in? The rate, or R, is still a rate, and we will still express it as a decimal. That's what we did on Friday as well for R. So express as a decimal, which means if it's a percentage, we need to divide by 100. So let's go ahead and also write divide by 100. Anytime you see a percentage, that's how you're going to get it to be a decimal. N is the number of times interest is compounded. Interest is compounded. And so this table here, this is representing what N would equal. And so we'll fill this out in just a second. T is still time, just like it was on Friday. For those other models, and so time, remember, just represents how much time in years usually, over what period of time are you leaving your money in this account for it to accrue that much interest. Okay, so N, this table here, and you'll want to make sure you know these words and what number it corresponds with, means how often is interest being added into your account. So yearly or annually just means one time. So the bank will figure out what's a good time. It could be the first of the year, it could be in the middle or the end of the year. They get to decide when, but they do it one time in the year, whatever interest rate it was. So if it adds up to like $5, they'll do it one time. Semi-annually means they'll look for 2 times in the year, because semi-annually means twice in that 1 year. Quarterly, think of quarters in a dollar. There are 4 quarters in a dollar, and there are like 4 quarters in a year. And so quarterly would just mean like every 3 months they would put something in so that you get it 4 times throughout the year. Monthly, there are 12 months in a year, so every single month they could decide when during the month, but you would get that interest put in. Weekly, there are 52 weeks in a year, so if you're not familiar with that number, definitely memorize that. Along with daily, there are 365 days in a year. We're not going to count like leap year and stuff, so 365 would be every single day of the year where they would put in an amount for your interest. So we're going to try a couple examples here, and we'll have to carefully read what word comes after the word compounded to decide what n is. So it says, for the first example, you're putting in $250 into a savings account that earns 4% annual interest compounded yearly. So ignore where it says annual interest. It's going to always say that because that's the amount of interest per year, the 4%, but they're going to compound it, in this case, yearly. So that's very similar here. But this could have said something else, and this could have also still said annually. So let's go ahead and try out in this example with this equation here, putting in all the numbers. So write a function that models the money in the account. That would be A equals 250, 1 plus, the rate we're going to write as 0.04 because you have to divide your 4 by 100. So if you need help deciding what to do there, we're putting 4 over 100 into the calculator. That's where we get 0.04 from. Okay, so that goes on the top of the fraction, 0.04 divided by, and then your denominator will be n, right? That's what this equation here said. So I'm using this equation, r over n, where n for yearly is just 1. So that doesn't really change anything, because if I divide by 1, nothing has changed. Then my exponent is also n times t, where n is still 1. It's the same exact 1, so these will always be the same number times the number of years, which I don't know yet, right? It just says to write a model, so I'm going to leave that t. So you can simplify this a little bit. It looks like this if it's simplified. 250, 1.04 raised to the t. That looks really similar to what we saw on Friday, because in this case, when it's yearly, it's not compounding it any more times than what we saw on Friday with the increase model, because it's just 1 plus that rate. And again, it will happen once in that year. So we want to know what happens after 10 years. Now, t is 10. So you use the previous example, and you substitute in 10 in for t, and you grab a calculator to see what it comes out to. For this part here, if you didn't want to simplify it like I did from here to here, that is okay, but at some point you will need to if it just says to write the model. You could have also just used a calculator to help you simplify that. All right, so we have 250, 1.04, and then you're raising it to the 10th power. So it comes out to $370.06. So don't forget a dollar sign. 370 and 6 cents, 06. So we started at 250. After 10 years, we would be at that much. No, it doesn't seem like much, but that's just it sitting in the bank account. Now, this is without making any kind of changes to the account. You can't add more money in or take money out. It's if this 250 it just stayed there for 10 years with this yearly interest, that's what would it come up to. Let's try another one. So the next one says 5 years ago, your parents put some money into an account to help you pay for college. And so it doesn't say how much money 5 years ago, but it does say that that happened 5 years ago. The account earns 2% annual interest compounded weekly. This is important here. They don't make any withdrawals or deposits, and now there's $55,257.50 in the account. How much money did your parents put in the trust account 5 years ago? So this is like we did see something similar to this where it's what you on Friday, where if you did not know the initial amount, we don't know P technically, we're going to use negative exponents here to find what happened before 5 years ago. Or you can use the same equation, but you'd have to switch where you're substituting in for P. So instead of putting it in here like I am now, you would instead put it in for A. But if you do this, as long as you're using negative exponents, that's good enough. So it's 1 plus, the rate is 0.02, because again, you have to take the 2% and divide by 100 to get 0.02. And then divide by 52 because n is weekly. And again, if you need that table here, weekly was 52. So then we keep going. 52 times 5 years ago. So that's a negative 5. And make sure if you're using a scientific calculator, you need this part in parentheses along with this part for the fraction as well. So I'll show you on a scientific calculator, but you could also use a graphing one. So here's how we type this in. 55,257 0.5, and then you have 1 plus, and then here's the parentheses for the fraction, 0.02 divided by 52. You're going to close both parentheses because it's for the 1 plus part and the fraction. Put a caret key, and then you're raising it to, you need to make sure there's parentheses for this, 52 times a negative 5. So once you type all of that into the calculator, you get $50,000 and just 1 cent. So your parents had put in $50,000 and probably not 1 cent, because that's just probably how the rounding worked there. But let's say they put in about $50,000 into an account 5 years ago. It grew to this amount with the 2% annual interest compounded weekly. So this is how much money there was 5 years ago. Okay, and then let's try out a few more examples on the next page. So on the back page, it's just one scenario, but we're looking at what happens for different types of N. So it says you deposit $2,000 in an account that pays 3% annual interest. So $2,000 is your initial, 3% we'd remember have to write as 0.03. And it says find the balance after 10 years, that's time, if the interest is compounded with the given frequency. So we're going to do 3 different scenarios here. So let's start the first one with 2,000, 1 plus 0.03 was R, over N is quarterly. So N is 4 for quarterly. If you need to look at the front table again, that's what that one told us. And then for the exponent, it's N times T. So 4 times 10, which we know is really just 40. But grab a calculator. Again, if you're using a scientific calculator, you need parentheses around the fraction, right here, its own parentheses, and then like I have it for the exponent as well. So 1 plus parentheses 0.03 divided by 4. Close both parentheses there. And then we have raise it to the exponent for 4 times 10, or you could have just written 40. And this comes out to 2,696. So don't forget dollar signs for your units. Oops, I'm sorry, let me write that again. $2,696.70 when you round that up. So that's how much money if interest was being compounded quarterly, that means 4 times in the year. What if interest was compounded monthly, 12 times a year? Let's see what happens. You're not going to change anything except for where N was 4. Now you're writing a 12. So we have it for the denominator of the fraction, and the exponent is now 12 times 10. So you're doing the same thing. If you're able to just go back and change, it's a lot easier to do this, but we can't always do that depending on the calculator you have. So that's a 12, and then the rest here is going to be 12 times 10. So it's easier if you don't have to retype the whole thing in. Oops, I think I made an error. Let's try this though again. 2,000, 1 plus 0.03 divided by 12, and raised to the 12 times 10. So that comes out to $2,698. So not a huge change, but definitely a little bit more, and also 71 cents here. A little bit more than this scenario where now you were getting it monthly. What about daily? Daily is $365. So let's see what that comes out to. Same thing, everything stays the same except for N. N is now $365. So for the denominator and for the exponent. And again, don't forget to put parentheses around your fraction if you're using a scientific calculator. So you have 2,000, 1 plus, another parentheses, and then this is 0.03 divided by 365. And then close your parentheses, raise it to the parentheses 365 times 10. And that comes out to, again, not a huge difference, but $2,699.68. So if you notice, they each increase kind of over time because we're compounding more often. And so the question at the bottom just says, which one's the best investment? Definitely getting it daily. And what conclusions can we draw from this is just that if you compound more often, you're going to have more money. So more money if compounded more frequently. All right, and that's pretty much it. And so you should have some time for homework. And again, if you have questions, just kind of hold on to them, write them down if you need to. We will go over all of the homeworks later this week.